Mr. Rempe has worked for 23 years at the Waste Isolation Pilot Plant, WIPP, underground storage of, is it low or high level or?
Intermediate.
Intermediate level radioactive waste. And that's near Carlsbad. And he continues studying the intersection of geology, mining, nuclear science, and environmental engineering. Mr. Rempe's got a BS in geology from Münster University in Deutschland, I'm in Germany, and he speaks fluent German.
Ausgezeichnet.
Yeah. He pursued postgraduate studies at the South Dakota School of Mines. His career has covered the geology and extraction of coal, potash, and petroleum, and also waste isolation in thick, deep rock salt. He's authored numerous professional publications, and he's given talks at lots of professional conferences. So he's a very well accomplished geologist. So let's give him a warm welcome.
Thank you very much for the nice introduction. Accomplished is what people call you after you retire. So I'm retired now. I'm hopefully going to tell you a few things today that you sort of think you might have known, but you never put into quite the same context that I'll try to put them in for you. And maybe I'll tell you a few new things. First of all, you see there's a logo for geologists, you know, the crossed hammers. But you see a little bit addition to that. You see the radiation symbol there. Without radioactivity and radiation, there would be nothing. Nothing would exist, including geology. Okay? And I'm just trying to make that point with that little handmade logo there. Of course, the Latin phrase up there, mente et maleo, does anyone know what that means? With a mind and with a hammer. Okay? Since we hammer as geologists on rocks. But also you should keep in mind the radiological, radioactive, and radioactivity connections with geology. So that's what the talk is about. One thing that we should do right from the beginning is we should have a rather skeptical attitude. And some of you may have heard about the book by Bjorn Lomborg, The Skeptical Environmentalist. And I just stole the title from that and put geologist in there instead. A skeptical attitude is a very healthy attitude toward everything that we learn and everything that we hear being taught to us. So I'm not asking you, like the preacher in the pulpit on Sunday morning, I'm not asking you to believe anything I tell you. This is not about belief. This is hopefully about facts and evidence. And if you have a problem with some of the things that I'll tell you today, please look them up afterwards. Not only is that presentation going to be on the web, but I'll also leave the presentation a PDF file with Professor Steinberg. So if you want to dig into it deeper later on, I put the sources for everything on the bottom of each slide. So you can dig into it deeper and look for yourself. So please don't believe anything I tell you. If I'm talking convincingly, then check it out yourself. We're going to slaughter, hopefully, a few sacred cows. And one of the most important one is this general belief that's out there everywhere, or pretty much everywhere, that ionizing radiation, the stuff that is radioactive, is mostly unnatural, unusual, always dangerous. That is a sacred cow that really does need slaughtering. And as you know, sacred cows make the best hamburgers. Just to illustrate briefly that the connection between geology and radioactivity is not something brand new. This is a book from 1928. So that was written only one generation after the discovery of radioactivity. You know, one of the reasons why so many people are afraid of radioactivity, because they think it's something new that didn't exist before basically 1898 or 1896. No, it existed all the time, but we have known about it only since the end of the 19th century. But one generation afterwards, there was already a book. It was published in German, but I translated it. It talked already in 1928 about the marriage between geology and radioactivity. And this marriage is something that even good, famous, and very well-versed geologists often don't realize. So that's what we're talking about. One other sacred cow that is out there is that nuclear reactors are something that is man-made, therefore dangerous, and we have to be it's very risky, and we have to be very careful about it, or we actually have to, say, forget it. I don't want anything to do with it. So this is from a publication by the American Physical Society, obviously done for kids in this sort of little rap or child nursery rhyme. Fermi built the first reactor, which was an important factor, blah, blah. No, Fermi did not build the first reactor. Fermi built the first man-made reactor, but Mother Nature had done it billions of years before him. And just to illustrate that, what is that big yellow disk up in the sky that keeps us warm? Sun. And what is that? It's a fusion reactor. Okay, so obviously Fermi did not build the first reactor. Now, Fermi built the first man-made fission reactor. There's fission and fusion, but he didn't even build the first fission reactor in the world, and I'll show you that later. So, the sun, our neighborhood fusion reactor. We're not going to go into details about, what all these reactions are going on there, but in the sun, essentially, are fusing two hydrogen nuclei and make helium out of them, and you have different energies being produced in that process. But whatever we call solar energy is nuclear energy. Okay? And as we will come back to in another slide, is all energies that we are using, all energies that exists, when you trace it to its ultimate origin, is nuclear. I don't care which one you start with. Trace it back to its ultimate origin. Without nuclear, there is no energy anywhere. And this is a slide actually published by the National Academy of Sciences, or that I got from their website, and it drives home the point. There's fusion in the sun, and there are some other processes, radioactive decay and fission, on planet Earth. And there's radioactive decay actually all the way through the universe. And these are the processes that drive our ecosystems, that drive everything. Here we have a slide from a book published in 1964, but there was a predecessor edition of that book that was published in the 1930s. This gentleman over here, Eric Zimmerman, he was a professor at the other university in Texas, UT Austin. And he had this in his book. And if you go back here, all the different kinds of energy, anywhere from the heat of the earth to tidal motion to solar engines to wind, daylight, vegetable, animal matter, whatever, oil, gas, everything else, if you trace it back, it's either direct solar energy, therefore nuclear energy, or indirect, because it was stored in between, or it was man-induced afterwards. But it all goes back to nuclear energy. So let's just, keep some of those essential basic facts in mind as we go on. And it doesn't matter whether it's inanimate or inorganic or whether it's organic. Everything without the sun or without nuclear energy just simply would not exist. Now, as geologists or geology students, and even as high school students who have taken, let's say, a physics class or a chemistry class, we have all heard about radioactive decay. If I have radioactive stuff, whatever it is, uranium, the nice example that Professor Steinberg just showed you earlier, or thorium or potassium, any one of the radioactive elements. I have a pile of it here, and I start out with it today. If I go into the future, it becomes less radioactive as a result of the process of half-life. It decays with a certain decay constant, and there's a so-called half-life. What most people, including geologists and actually including all natural scientists, hardly ever think about is that if that process goes that way, if you then basically do the same thing that we do as children when our mother teaches us, before you cross the road, look left and look right. If we look not only right in the direction of decay, but if we look left and say, well, if we start here and it becomes less radioactive into the future, it must have been more radioactive in the past, obviously. That's what that principle says. Which means whatever radioactive stuff we have today, uranium or thorium, potassium, there must have been much more radioactivity in the past. That means Earth history, way back when, must have provided much more radioactive environments than the one that we are living in today. Which means, since we know that biological evolution started 3 billion years ago, it started under much higher background radioactivity than what we are exposed to today. Which should put a big question mark right there in our brain. And that says, I have heard so often that every little bit of radioactivity ought to be avoided because it's bad for you. How can that really be if where all life started there was much more radioactivity than we have today? Isn't there some sort of discrepancy? Just a little food for thought, and that's actually what that statement there says. Please disregard the name of the fellow down there. I have shown this quite often and people said, oh my God, a guy with the name Looney. I can't do anything for my name, okay? He said something very valuable. And just to illustrate it in a more scientific way, this is from a book, and I have several books out here, and you're welcome to look at them after the talk. By the way, this particular book is also on the web, that's why I put the address down there. I have mentioned several times the main radioactive elements here already that we have on planet Earth, and actually on planet Earth or in the solar system. Uranium, 2 isotopes, 238, 235, then thorium and potassium. Potassium, 1 isotope of that. If we just go to the present here and we say, we just arbitrarily set the quantity or the radioactivity of each one of those at 1. Then if we go back 200 million years and 500 million years ago, the Earth is 4.5 billion years old, so 4.5, then that radioactivity that today is 1 would have been way back when there 2, it would have been 128, it would have been 1.29, not that much difference because the half-life of this thorium isotope is huge. And even here with the innocent potassium, it would have been 14 times as much. Does anyone remember where potassium is as far as geologists are concerned? Potassium is a big ingredient in feldspars. And feldspars are the main mineral that we have in the Earth's crust. There isn't a mineral group that is more representative of the Earth's crust than feldspars. So we know that the crust must have been much more radioactive in the past than it is today. And this is another illustration that shows basically the same thing. It shows a slight decrease here in radiation over time during Earth's evolution. Okay? It doesn't really tell you anything new beyond the slide I just showed you, but it shows you a name, T.D. Luckey. T.D. Luckey was a professor at the University of Columbia, Missouri, who wrote in 1980 and 1992 big books on radiation and a reasonable approach to radiation, published by CRC Press, which is quite a reputable academic publishing company. And if you want to dig deeper into some of the subjects that I'm just touching on today, I highly recommend looking him up. Just Google him. So, we know that life started with much more radiation than we have today. It evolved in a radiation field. I put in there in parentheses vitamin R, called radiation, because we had a higher concentration of radioactive elements, and we'll talk about we had actually natural reactors, and the natural background radiation on Earth varies today by at least 2 orders of magnitude. We'll dig into that a little deeper. Higher concentration of radioactive elements, the first point up there, actually there were some radioactive elements present during the early Earth history that have decayed since then to basically nothing. We can't detect them anymore. So there are fossil elements that don't exist today anymore. And we know that from studying the ways that radioactive decay goes on. One thing that we hardly ever think of it, but there's a connection to astronomy, as the spiral arms of our galaxy just rotate, I think about once every 250 million years or so. They go occasionally through areas of intensive star creation, and those are much more radioactive than the rest of the universe. So in these regions, sometime in the geologic past, Earth was probably exposed to about 10 to 100 times more radiation than we can actually calculate based on just this backward extrapolation of radioactive decay into the future. It must have been more radioactive in the past, but then in addition to that, we probably got a whole pile of additional cosmic radiation that could have changed, for example, evolutionary paths, or could have accelerated or somehow affected them. So that was just the introductory stuff. Now let's go to a scientific mystery. Has anyone ever in this classroom heard of OKLO, O-K-L-O, that big word up there? Okay, that's when I usually tell people, if you have ever taken a class in any one of the natural sciences, whether in high school or in college, and you have never heard this word, sorry for the teachers in the audience, you have a darn good reason to sue your educational institution for malpractice. The reason being that this is one key scientific fact that if you don't know about it, you are missing a huge part of the overall picture. Let me start with this fellow. Paul Kuroda was a Japanese-born scientist. You see the years there. And he was inspired in the 1930s by lectures that were given by Francis Aston, who developed the first mass spectrograph, and by Niels Bohr. Some of you may have heard of him. He was the guy who actually came up with the atomic model. He came to the United States. You don't need to write this down. You can find this on the web if you just Google his name. Became a US citizen. He taught chemistry at the University of Arkansas, and he published in 1956 a paper where he said, well, based on this fact that if I go backwards with radioactive decay and things were more radioactive in the past than they are today, I can postulate that at one time in the past, uranium deposits might have been rich enough that under the right conditions, they might have actually started by themselves a chain reaction as we have today in nuclear reactors. And he just published a 2-page paper, and it was rejected by several journals before it was accepted. And nobody paid any attention to it, 1956. He said, these reactors are possible under the right geochemical and geological conditions. And by the way, he was a very humble guy. He was not arrogant at all. You see that quote there at the bottom of that slide? He didn't just badmouth 99% of the students. He said, I was one of those 99% that are just sitting there and basically not paying attention. And nevertheless, he came up with this paper. And in 1972, in a little place in West Africa, in the Republic of Gabon, at a place called Oklo, a uranium deposit was found that actually the uranium deposit had been found years earlier. They were mining it. But it was found that in that uranium deposit there were areas enriched in uranium very high, with a very high degree of enrichment. But there were some isotopes missing that should have been there. And when people saw that, they thought, well, maybe somebody actually squirreled away some uranium there to build some illegal nuclear weapons or Lord knows what. So they investigated it, tracked it back, and they found there must have been 2 billion years ago nuclear reactors going. Otherwise, we can't explain the waste products, the fission products that we find in this neighborhood and that are in that uranium ore. By the way, for those of you who remember or may have heard the name Albert Schweitzer, he was a missionary to Africa and a philanthropist, and I think he got a Nobel Peace Prize in the 1950s. That's a picture of him, and he was in a place up here on the coast of Gabon, so that you know where to place this area. So, in 1976, you see it up there, Scientific American, July 1976, there was actually a paper on that. Natural fission reactor, and it was written by George A. Cohen, who shortly before he died looked about like this. And he was a scientist at Los Alamos National Laboratory in New Mexico. And he published that article in 1976. Nevertheless, the story about Oklo is hardly in any textbook today. There's no excuse for that. Has been known since at least 1976. Scientific American, not an obscure journal somewhere in Timbuktu, okay? So he said at the time, man was not an innovator, but just an imitator of nature. He also said in an interview that he wrote, that he gave to the Los Alamos paper a few years before his death. At first I thought it was a phony. People didn't believe it. But he published that article on these natural reactors. In 2005, another article on Oklo was in the Scientific American, The Workings of an Ancient Nuclear Reactor, by a fellow at Washington University in St. Louis, originally from Russia, Alex Meshik. And they worked out exactly the way that these reactors operated. There was a uranium deposit, highly enriched in uranium, and water was percolating, groundwater was percolating through it. And the water serves as a moderator that can start a nuclear reactor going. So when the water ran through it, the nuclear reaction started, the reactor heated up, this uranium ore, this pile of uranium ore heated up. When it heated up, the water turned into steam. And when the water turns into steam, steam is a very bad moderator. And so the nuclear reaction stopped, it cooled down until it was cool enough, the water came in there again, the reaction started again. So it cycled off and on for 150,000 years in 30-minute pulses with 2.5-hour dormant periods, consuming 5 tons of uranium. So we prove that nuclear fission is natural. It was not made or invented by Enrico Fermi. And it suggests that if we continue to look, we may find some other reactors. By the way, at this location in Oklo, there were on the order of, I believe, between 15, 16, 17 of those little reactors. Each one of them about the size of a pickup truck. Not big ones, okay? But nevertheless, they ran. So we know nuclear reactors were not invented by people, whether fission reactors such as Oklo or fusion, the one in the sun. There's, by the way, a few pictures of that uranium mine there in Oklo. And by the way, any reactor produces radioactive waste. And the radioactive waste that was produced by these reactors didn't migrate for more than a few feet or tens of feet away from it. So, which proves that actually radioactive waste isolation, even just left to nature, works very nicely. Just add a little Yankee ingenuity to it and we should be doing just nicely. There is not really any reason to spend billions of dollars on taking care of radioactive waste. Mother Nature has actually shown to us how it can be done. I'm going to skip over that quite a bit, but Oklo is really nice as an analog for radioactive waste disposal because everything was far less than ideal than we can make it, for example, in the place where I worked for 23 years. Okay, so that was that little detective story that I threw in there. Back to more general principles. We now realize that Earth has been radioactive from the beginning. It has been more radioactive in the past. As a matter of fact, that's valid for the entire universe, pretty much. And as a result of all of that, if we dig 1 foot deep anywhere on the planet on average, of course, nowhere is there a real average, it's a little more here, a little less there, but on average, people have looked at that. If we look at the concentration of the principal radioactive elements that we have on planet Earth, uranium, thorium, potassium, radium, and radon, then if it all adds up in that 1 foot deep, 1 square mile of that, there are 17 curies of radioactivity. Let's not get hung up on units here. Curie is a non-metric or non-standard unit that we use still in the United States, and then the becquerel, the BQ, is the international unit. And you can see one thing right up front here, down here. If you express something in curies, it looks like an innocent little number. If you express something in becquerel, gigabecquerel, that's million becquerel right there. Okay? So if you hear about radioactivity and if you don't hear any number associated with it, be always highly skeptical. Because as Robert Heinlein, the famous science fiction author, once said, if it ain't accompanied by a number, it ain't science. And the other thing is, when you see big numbers, remember oil spills. How do they count petroleum when you have an oil spill? They say so many million gallons. How do we usually count crude oil? Barrels. Why do they use the gallons? Because it makes it more dramatic. Okay? And it's sometimes the same thing. By the way, when Dr. Steinberg here came in with the radiation detector earlier, and he approached you with it, and there were a few clicks. If you took a measurement of each one of us, on average, each one of us is a radioactive source of about 8,000 becquerel. That's because of these radioactive elements that we have in us. For the most part, K40, potassium 40. Potassium is, without potassium we die. But there's traces of these other elements in us too. If you add them all up, 8,000 becquerel, each one of us is a source of that. So we are all radioactive. Now, we talked about the distribution of radioactivity over geologic time. Planet Earth was much more radioactive in the past than it is today. But the distribution of radioactivity across planet Earth is also not even. It's not average. There are some places that are pretty much sort of average, such as mostly in the United States. And the units, again, milligray per hour, you know, don't worry about that. You can look them up, you can Google them. But the relation between the numbers here matters, not the absolute numbers. In the USA, 0.4, and then the maximum value would be 0.8 or 0.9, even closer. But there are areas in the world, such as Guarapari, these are beach sands in Brazil. Kerala, these are also beach sands in India. And Ramsar, Iran is the highest in the whole world, where you have, instead of 0.4, you have 10.2, and the maximum, instead of about, let's say, 1, is 260. It tells you that the natural background radiation on planet Earth varies over 2 orders of magnitude, 1 and 260. 2 exponents of 10. Okay? Now, people have looked at, or researchers, scientists have looked at people who live in these areas to see, are they affected by that? Do they live less long? Do they have more cancers or any kinds of other diseases? And there is no evidence, not one shred of evidence, that people who live in those high background radiation area are any worse off than the rest. Actually, there are some indications they are somewhat better off, which is counterintuitive, because we all know radiation we want to avoid. If we get more of it, it's going to go. These people get a heck of a lot more, 2 orders of magnitude more, and they're doing at least as well as we do.
What's the source of the Iran radiation?
Come right to that. Thank you. Beautiful setup. Thank you. This is what average on planet Earth is normal. Again, don't worry about the units, becquerel per liter. You can look those up. And what they have in Ramsar. The source of this is, these are warm waters. This is basically a spa. And Ramsar is right there on the beach, on the shore of the Caspian Sea. And there's water coming, and that percolates through granites that are very high in uranium and thorium. And they emit radon. And that radon really gets loaded into the water, and that's the main source of this exposure. Okay?
We're talking about alpha, beta, and gamma?
Since it's uranium and thorium, it's, I guess, mostly alpha. But the point here is that even if you normalize alpha, beta, gamma to the dose numbers, and we might spend some more time on that, it's still, you know, a dose is dose. And you have the dose weighing factors for those different things.
Was there any particular reason that they did do any research in Africa?
Well, they did research on Oklo, but you're mentioning, you're thinking more about there's no location on here in Africa. Because Africa, as far as science is concerned, with the exception maybe of South Africa, is still, unfortunately, a very dark continent. And I'm really glad you asked that, because since these natural reactors were discovered there in Oklo in Gabon, I wondered, well, you know, what is Gabon doing on studying this? And, you know, what are the local universities doing? And unfortunately, there's very little. There have been Western scientists that went there, but Gabon has apparently been a country where, yeah, there is a university, but, you know, that's named after the first president over there, who was sort of an autocrat, and so science is not given a very high priority in the country. But I was exactly wondering about that. You know, if I had something like that in my country, then I would think I would build a research center that's based on, you know, this unique in the world so far finding, but unfortunately there's very little there so far. So that's a place with the highest known radioactive background in the entire world. So let's look a little bit at radiation exposure and radiation regulation. We have up here a scale that goes from 0 to 5 rem or from 0 to 50 millisievert, just to illustrate that you can count it in either conventional units or in the international units. It doesn't really make much difference. That small area right down here got expanded up here. And you see, this is the area from 0 to 1 millisievert. Right there, that small area got expanded. This is what the exposure to nuclear power amounts to. This is what Chernobyl amounted to. But this is what medical diagnostics amounted to. But nevertheless, all of this here on that scale is squeezed into that little space. However, look at where our regulations are. The EPA, General Population Water, EPA General Population Air, Yucca Mountain Project, NRC, Decontamination and Decommissioning. This makes absolutely no sense. Okay? We are regulating way below natural background. See the natural background up here. World average, 2.4. US Rocky Mountains, if you live in Denver or Leadville, Colorado, you get even more because of less air on top of you and more cosmic radiation exposure. In Sweden, Brazil, Kerala, and Ramsar that we talked about earlier, that's way off the scale. That's 5 times as much. That's to the roof of the building. And we know that people suffer no ill consequences as a result of that. Nevertheless, we're regulating down here. We're spending gazillions of dollars on regulating something that is way below background, for which we have no evidence that anyone has any benefit from it. Because we have this concept, every little bit of additional radiation is dangerous. So that's a conventional radiation symbol. You might still have it around some labs here in this on this campus. Or let's say if you go to some medical procedure at the hospital, that was already pretty, in my opinion, almost meaningless, because everything is radioactive, including I myself and every one of you, the 8,000 becquerel that I mentioned earlier. But this modern radiation symbol, this replaced this one, so we'll see more and more of that. This one is even worse. It says if anything is radioactive, and it doesn't give any number, any quantity, nothing to compare with, it says it's deadly or potentially lethal. Run. I have to run from myself. And even that wouldn't help. I have another slide of a cemetery. I can't even kill myself and take care of the problem, because now that cemetery is a radioactive waste repository. Since I'm radioactive with 8,000 becquerel and they put me 6 feet under, now that's a radioactive waste repository. So obviously I still haven't solved the problem, right? It's silly. Once we start really thinking about that, independently thinking about it from a skeptical perspective, some of these things look totally foolish. Back to the area where I spent 23 years of my career, Geologic Repository for Radioactive Waste. There are 2 places in Germany called the Asse and Morsleben. And the Asse is depicted here, which is a salt dome similar to the ones that we have along the Gulf Coast here in South Texas all the way through Louisiana, I think even one into Alabama. And radioactive waste has been put on the order of, well, all the way down to 900 meters here into various portions of that old salt and potash mine. Now, people have made a big deal about that the Asse has some groundwater seeping into it, and that the mine might get flooded, and that radioisotopes from the waste might escape to the surface. What they don't consider is numbers. And here's a picture, idealized picture, of the Matterhorn in the Swiss Alps, consisting mostly of granite. And granite, as we just mentioned, is radioactive. It has uranium and thorium, especially in the ferromagnesian minerals built into it, the dark ones. And this volume of Matterhorn that is exposed basically above the surface, that has in it 10 to the 16th becquerel of radioactive stuff in it. Okay? The radioactive waste that we have in those two German repositories, buried about 700 meters below the surface, so not exposed to the air, amounts to this, if we add them both up. So we worry about what we have in there. Well, why don't we just put barriers all around the Matterhorn and say, don't ever climb this mountain, you're going to kill yourself. maybe by falling off the rope, but not by the radioactivity. So this shows the whole thing, or shows a different aspect of the same issue. And that is a schematic picture of the Asse. So you have a shaft, and you go 700, 800 meters down, and there is the waste right here in the old mined out chambers in the salt mine. Well, the waste inventory, there's so much uranium, thorium, and plutonium in there, and the activity of all of that, of course, it decays over time. In 2000 was 3 times 10 to the 15th, in 2140, so 100 plus years from now, it will be 3 times 10 to the 13th becquerel. Now let's look at the rocks that is on top of that repository, the overburden that I have to go through in the shaft before I get actually to the mine down there. What's the natural radioactivity of that? Remember that 1 foot deep, 1 square mile, how much radioactive stuff is in there on the average in the Earth's crust? If we just take those numbers and add that all up, that means we end up with roughly, since by comparison to this year, these other numbers hardly matter at all, on the order of 10 to the 15th becquerel right there. So that means the overburden is just as radioactive what I got down there. So any idea of if there are any problems with that repository down there, to get it all up back to the surface and thereby save mankind, there's no basis for that idea. That groundwater that circulates through here is going to bring the same amount of radioactivity up there as any water that goes into the mine and then percolates up. It's a no, never mind. Which really leads to the conclusion that if you need to take care of dangerous waste, radioactive waste, if you bury it just about anywhere, throw it out at a map, 500 meters or deeper, it's not going to come back at you and hurt you to any measurable degree. Something that's sort of paradoxical on its face is when we go underground at WIPP, the place where I work, that's 2,150 feet below the surface. That's one of those rooms. We measured the background radiation down there. You see right here what it is at the surface, and you see what it is at the underground. And you see WIPP is actually a radiation-deprived environment. People who work down there, they actually get less radioactivity or less radiation than if they worked up at the surface. The reason being, they got 2,000 plus feet of rock shielding them against cosmic radiation from space. They don't get it. So if there is any contamination set loose in WIPP, in that repository, as has been done 2 years ago, if you don't give me numbers that tell me by how much did they increase the background and how does that compare to what I get on the surface, if you don't give me a number, you have not justified to me spending $500 million on so-called remedial measures. And that's one of the issues that is going on at WIPP right now. And I'm not going to belabor the point here. I'm going to stay after the talk as long as anyone wants to talk about it, and we can go into that at that time. But in essence, an underground environment such as WIPP, where you have salt, a rock that has almost zero radioactivity, such an underground mine acts as a filter. Whatever radioactive stuff is in the air, it gets plated out, it sort of attaches to the walls, it doesn't come up to the surface, which is why when we measured the radiation between the intake shaft, where the air enters the underground, and the exhaust shaft, we found out it's much higher where the air goes into WIPPs than where it goes out. This is a radioactive waste repository. Less radiation coming out than goes in. So when WIPP had its contamination case 2 years ago, they allowed people only in protective clothing in here. And what I did here is I basically just at random mixed a few pictures of people who are dealing with Ebola patients or dealt with Ebola patients, and some pictures of people at WIPP that go underground. And then I dare you to figure out which is which. And the risk at WIPP, as I just mentioned, is probably close to zero. And Ebola, now that's a nasty way to go if you get it. Okay? But we are approaching them both with the same order of caution. Does this make sense? Just to let you know, that one is WIPP, that one is WIPP, and I think the rest is Ebola.
Yeah.
So,
What was the leak? What happened?
let's talk about it afterwards, because otherwise, but there was a leak. And this was what the management operating contractor's general manager at the time said: if I can avoid 1 additional millirem, I will. You saw that scale earlier. The radiation varies by 2 orders of magnitude on the surface of planet Earth, and he is worried about 1 millirem. And he's going to spend mine and your money on it. And that radon is the largest cause of lung cancer, there's no proof for that statement whatsoever. So let's be skeptical. Okay, and just in case anyone does not thinks this is just here, you know, put in there for the gag value, here's a book, and this was published by a professor at Princeton University, and that's Princeton University Press that published it. I really recommend this little booklet. There are some suggestions. Well, we'll jump over that one. What everything we have talked about so far should have made clear that when we're dealing with so-called controversial things, we need to think about them in a skeptical way. And once we start doing that, and in a rational and skeptical way, we may find out something like this. In radiation protection, rather than spending billions of dollars, we may get some more. We may get a lot more benefit by first thinking about what is it that we're doing and what are the comparative risks. How does the risk from a little bit of additional radiation compare to the risk of running off the road on a highway that doesn't have any shoulders, for example? So I'm attaching this statement to every one of my emails because we need to continuously question and justify everything that we do as people who want to be taken serious as scientists or as human beings, for that matter. I do remember, some of you do not, or most of you do not, but in the 60s, during the time of the student revolution and those kinds of things, when there was unrest in the country, it was, you know, don't trust anybody, or, you know, don't take anything on face value. It's a good general rule, okay? The bumper sticker was question everything. Very good advice. So what are the practical results of this, of radiation varying so much in time and in space, and us protecting against these real tiny little things on the bottom of the natural variability? What are the consequences of that? The consequences are that, for example, the Department of Energy is cleaning up a whole bunch of sites around the country. If we clean it up to 100 millirem a year, or to 25, or to 15, or to less than 10 millirem a year, this is what the cost does. 100 millirem, remember, we are exposed in the United States to natural background each year of about 360. That is natural. In addition to that, we'll get about 200 to 300 more on average from medical procedures. So if you regulate to 100 millirem per year, that is far less than any one of those. And that would cost $35 million. But if we go to 10 millirem, it would cost that much. So you can see this has very significant implication on how we spend our government money. And of course, there is no such thing as government money. It has very high ramifications for how do we spend our money, because every dollar the government spends, it first has to take out of our pockets. So we as citizens have a significant economic and of course scientific interest in how we deal with these issues. For those of you who like curves better, or pictorial description here, the cleanup cost for US Department of Energy facilities right now is estimated $350 billion, and that estimate is about 10 years old. So by now it's probably at least twice that much, because anytime the government estimates anything, they never live within the budget. And if we clean up to, let's say, 350 millirem or to 50 millirem, we can save so many billions. And you know, whatever number you want to throw in here, whether 10-year-old number or today's number, the curve is going to look exactly the same way. What are we going to clean up to? 15, 25? If we clean up to much higher levels that are still well below the lowest background that we have in the United States, we could save quite a lot of money. So it's very significant. It's not just some academic discussion. Another picture to show you how we regulate things. We have from 0 to 100 rem, and here we have 0 to 2 rem. So again, we got the first two up here, enlarged here on the bottoms there. And you see how much exposure we regulate, the EPA regulates. We see natural background, Kerala, and there's Gorapari, and there's Ramsar over here. So does that really make sense to have standards down here when the natural background is up here on an exponential scale up here? That's, again, this one goes from 0 to 2, this one goes from 0 to 100. And now back to the slide that Dr. Steinberg used in printing out the invitations to this seminar. The Department of Energy itself, the Office of Biological and Environmental Research, Office of Science, they published this chart. Here again, you have different scales. This on the bottom here goes from 0 to 100 millirem. This one from 0 to 1,000, 0 to 10 rem, which means 10,000 rem. Millirem, I'm sorry, and then 0 to 100, 0 to 1,000. So we are increasing it. Now, you see again, all these red numbers, these are our regulatory standards. We regulate down here. Now there's a natural background in the US. We are regulating even below the natural background in the US. Again, the average exposure to US citizens is not 316, but it's about twice that much, mostly because of medical procedures. But there are areas in China, Brazil, Iran, etc., that are much higher with no evidence, and that's the key word. Let's have the evidence. If somebody proposes something to protect us against something else, let's have the evidence. What's the evidence on which you base your standards? And if you cannot come forth with evidence, then you haven't made a case. You know, we are talking so often, well, let's see the science, you know, and I'm almost allergic, you know, again, to this word, well, let's look at the science. Let's just look at the evidence. You know, when the detectives on some crime show on TV talk about, you know, who did what and when, they don't talk about science, they say evidence, and simple evidence, that's what we need. We need evidence for what we're doing, or we should have anyway. So the first, by the way, picture here shows it in REM. That is in the US still the conventional unit, and the other one in Sievert. But it's the same story in both of those. But I put them in there both. Couple things sort of to wrap it up. In 1961, only 8 miles away from WIPP, near Carlsbad, 30 miles outside of Carlsbad, we had an underground nuclear test, so-called Project Nome, where civilian applications of nuclear detonations were investigated. 3 kiloton device set off about 1,200 feet below the surface. What happened was that some of that radioactively laced steam came up. This is a picture from Life magazine from January 62, so a month afterwards. And that radioactively laced steam drifted in a northwesterly direction across some highways toward Artesia, New Mexico. Nobody got hurt by it. Now, it was something unintended. We should have avoided it. We didn't. But it didn't hurt anybody. This is what it created. It created an underground cavity. There's a minor for scale. And again, that was in December 1961. And the first people entered the detonation cavity only 6 months after the shot. And again, none of them had any effects that we can pick out of the statistics that he lived, you know, shorter life or had more cancer or got it earlier or anything like that. Now, this was unintended. We should avoid it. But nevertheless, even this didn't have any evidence for measurable negative consequences. So, we often hear when we deal with radiation, radioactivity, or other controversial subjects that let's be careful. Let's apply the precautionary principle because while we may not be sure that there is a real danger there, let's just err on the side of caution. We hear that with many things and too many to mention. So I wanted to give you a little historical excursion. 1450 to 1750, they used to burn witches in Europe, and a few were hanged in Salem. But nobody had any evidence that witchcraft existed. Nobody had any evidence that witches existed. But the precautionary principle at the time told the people, well, we are not sure witches exist, we are not sure witchcraft exists, but let's just be careful. just in case they exist, and if we have some suspicion that somebody might be, we would rather burn a few than to subject society to the danger or the potential danger from them. And most pictures about witches and witches being tortured and witches being burned, that's sort of abstract. Okay, we're just looking at it, well, poor woman, okay. This lady has a name, Anneken Hendricks. She was burned like this in Amsterdam in 1571. These are real people who became the victims of an unreflected precautionary principle. And I submit that when we spend, let's say, $500 million on a danger that does not exist in, for example, cleaning up a radioactive contamination that doesn't hurt or harm anybody, that $500 million is not available to put shoulders on that rural highway where the next person that gets a little sleepy gets off, rolls over, and is dead. How are we better in using money on non-existing or on hazards for which we have no evidence? How are we morally different from our ancestors who did this? And again, to increase the skepticism a little bit more, or maybe to drive home the point we should be skeptical of everything we hear. Steve Hawking, eminent physicist, great guy, has done a lot of laudable work. He's quoted here as saying the trip to Mars or space travel would not really work too well reaching distant planets because the radiation exposure would be too severe. He was quoted just on the internet. I'm not saying that he did that. I didn't check whether he actually did say that, but let's just assume he did say that. That's a picture from National Geographic, January 2001. And by the way, you won't find, or okay, not you won't find. I tried hard, and I did not find in the literature that I can access through the internet anything on this. But I found it in National Geographic, more or less by serendipity. This shows you the dose in millisieverts, and it shows you various kinds of background radiation that people are exposed to. So background radiation on Earth, a nuclear worker might get that much, a space shuttle crew over 10 days might get that much. If you stay at the Mir station or the space lab, you might get that much. And then it has this figure there. This would be a Mars mission. 1,000 days, let's make it a round number, let's say 3 years, round trip to Mars. And that exposure right here, 1,000 millisieverts. On that scale that I showed you earlier, where we regulate, Ramsar is at about 260. And that's for 1 year. Multiply 260 times 3, and you're pretty close to those 1,000. And there is this widespread opinion out there that when we go out to Mars or other interplanetary missions sometime in the future, there would be too much cosmic radiation. You would have to build lead-shielded cabins for the astronauts, and of course lead is very heavy, and so you got a problem in getting that one still lifted off Earth and that sort of thing. And therefore, high radiation space environment really makes it almost impossible to travel to other planets. But people make these statements without looking at the numbers. And when you look at the numbers, you see that's well within the range of what people get exposed to here on Earth. Remember, in Ramsar, that's the highest known area of planet Earth where people get that high exposure. There might be others that are even higher, and we have no indication that, let's say, 2 times as much as Ramsar is going to harm you. So this may be, most likely, this is just as harmless as people living in Ramsar, Iran. So I feel very optimistic about travel to Mars. And I asked actually Robert Zubrin, who wrote a book, Mission to Mars, and who is an expert who has worked with Jet Propulsion Laboratory and NASA and whatever. And I asked him about this diagram, and I said, do you have anything that disproves this? That tells you that space travel and the radiation you get from space there is really, much more of a problem? He said, no, I have no other evidence for that. James Lovelock is a famous environmentalist. He was one of the founders of Greenpeace, and he published, there are a lot of formerly anti-nuclear people, so-called environmentalists, that have come around to look more favorable at anything nuclear. And he made that statement. So let me close with this one. The same logo that we had at the beginning. And not only is an anti-nuclear geologist an oxymoron, but since everything is based on radioactive and nuclear processes, any anti-nuclear scientist is actually an oxymoron. I don't care whether it's a geologist, biologist, chemist, physicist, any one of those. And thank you very much for giving me this opportunity. I will stay as long as it takes.